Hello everyone. So in this video, we're finally talking about Python syntax regarding classes and objects. So before you try the things in this video, before you watch this video, you should try Python introduction first, where uh, you try the basic syntax of Python. So I'm assuming that you've already watched that and you've already done the MP related to that. Uh, yeah. Okay. So Python was never originally meant for pure OOP, but OOP is not a classification though. It is a paradigm. It is a set of ideas. It represents some kind of worldview. The language does not make the OOP elegant. It is how you adhere to the design principles of the paradigm. And this is the reason why when I teach the concepts of OOP, I try my best to not include code with it. But uh, it is inevitable that we will discuss code relating to OOP. For this specific course, we're gonna be using Python. This is what I did in uh, the last time I taught this course as well, which was the first time actually. So creating classes in Python is very easy. So here is an example of an empty class, and we're calling it empty class. So in Python and other OOP languages, naming classes with nouns that start with capital letters is a convention. Hence, you see this class right here called empty class starting with capital letters. You can name it with weird names, but correct naming is a good practice for maintainability. So as much as possible, the name of your class should be short and should be descriptive as well. And again, the convention is that class names start with capital letters. So you write this Python keyword, Python expression pass right here to indicate that the specific scope is empty. By putting pass inside classes, the classes will have no attributes, methods, thus it becomes an empty class. So that's why this is an empty class, because it just contains this expression pass right here, which again indicates that this has nothing in it. So to make this class more interesting, let's put something inside it. And you can put methods and attributes inside classes. Everything found inside the indent level of a class belongs to that class. So we have here another class called VoiceBox. Now this one is not empty as well. And again, everything found inside the indent level of this class right here, which is this line, this line, this line, and then this print right here. So these three lines belong in this class. So when you call voicebox.speak right here, to do that, I'm gonna uncomment this one right here, save it, and run it. You'll notice that Python prints, "Hi, I am Vincent, the voice box." What is going on right here is that the dot speak is this reference right here is specifically the speak method found inside the scope of class voicebox. So specifically this speak function right here. So the function accesses an identifier called voicebox.name inside it. So if you notice right here, you find voicebox.name, which is an identifier specifically found in the class voicebox, which refers to the identifier found again here. So this identifier is named name, and its type is string, and its value is Vincent. Therefore, when voicebox.speak is finally invoked, what is going to happen is that it concatenates voicebox.name to these extra string literals right here, giving you the print, "Hi, I'm Vincent, the voice box." And that's the only thing that it does, because it is a voice box. It speaks. So I also uncommented another line right here accidentally. I was supposed to uncomment that later. But anyway, this other line right here, you see voicebox.name is equal to Vito. When this is executed, it changes the value to Vito, which was originally Vincent. So this one right here is a mutation of the string name. This is a destructive assignment to voicebox.name, replacing the original value Vincent into Vito. So whenever I uncomment this part right here, which is calling voicebox.speak again, and rerun the Python file, I'm gonna get a different print for the second call, voicebox.speak. It now says, "Hi, I'm Vito the voicebox." Because in between this call and this call, we have changed the value of voicebox dot name. That makes sense. So the usage of this specific usage of classes right here that you're seeing right now is actually not interesting at all, Yapon. Even though it contains attributes and methods, this class is merely used like a data holder lang. The attributes and methods you see inside VoiceBox right now are what we call static attributes and static methods. We won't really use a lot of static attributes and methods in this course because it is not actually a good practice to use them. Basically, statics are attributes and methods that are not associated to class instances. They exist in the class itself outside the lifetime of any instance. So supposedly, the values for attributes and the invocations for methods, they are supposed to be associated to a specific class instance. In this case, what we're doing right here, we are associating voicebox.name or the attribute name to the class itself, not to a specific instance of voicebox. We are associating speak not to a specific instance of voicebox, but to the class voicebox itself. And again, the reason for that is because we are implementing them and uh, declaring them like static attributes and methods. So right now, the VoiceBox class is unable to create meaningful instances or what we call objects. So if we try to, uh, give me a second. If we try to uncomment this line right here, which is creating an instance of VoiceBox, calling it V of type VoiceBox, and then instantiating VoiceBox right here. If we run this Python file right here, that's not what I'm trying to do. Save and then rerun OOPython.py. Nothing meaningful will actually happen because if you notice right here, this instance V doesn't have specific attributes for itself. What has attributes in this case is the class itself, not the instance V. So uh, again, this is not actually interesting at all, and we're not actually gonna create uh, a lot of static attributes and methods in this course because it is not really good practice. So let's make a new class, one that can construct meaningful instances of itself. And to do that, we have to use a special constructor called the init constructor. You can see it right here in the third class, which is this class called robot right here. This is a reference to the example that I used in the previous lectures about specializations. This is normal bot. I just called it robot right here. So this is a new class called robot, and you have here a special method which is responsible for spawning instances of the class. This method right here is called init. And if you notice right here, this init is surrounded by two underscores. Special methods in Python are usually created like this. They are surrounded by double underscores. So, looking at the code for this one specifically. Let's look at the code piece by piece. First, the init method that you see right there. Uh, Here you'll notice a special identifier called self. This one right here, self, is a special identifier. The identifier self is a special reference to the instance of the class using it. You're gonna see what that means later when you actually create instances of robot. So basically, whichever instance is being spawned right now is assigned to this uh, special reference, which we call self. It doesn't actually have to be named self. You can actually name it anything, but naming itself is a Python convention. Again, self refers to itself or the instance that is being spawned right now. And what are you doing to the instance being spawned right now? The instance being spawned right now has the attribute called name. And that attribute called name, by creating this assignment right here, it automatically creates an allocation for the attribute of name. Self.name is assigned the value n, which is the value being passed to the constructor right here. So this actually, this n right here refers to the value that you pass to the constructor, and whatever that n is, it is then stored to the attribute self.name. Oops, almost dropped my microphone. Okay, basically, Python understands that the first identifier found at any non-static method is a reference to the instance invoking the method, by the way. So again, it doesn't have to be named self. It could be named any arbitrary name, for example. Python will understand that whatever is the first instance that you place in this list of attributes, the first one will be the reference to the instance. So inside, we are preparing the instance by assigning values to its attributes. And we do that again by assigning this n right here to the attribute called self.name. Since name is dot reference to self, which is the instance being spawned, the instance automatically gains the name attribute. And unlike the example a while ago, voicebox.name right there, this attribute is associated to an instance of robot, not the class robot itself. If you do it like this, robot.name, this one will refer to the instance owned by robot, while self.name, sorry, not the instance named by robot, but the name owned by robot. But if you dot reference it like this, self.name, this name is the name specifically owned by the instance of robot. So dot referencing is similar to what you do with C structures. If you have structures and you want to access the specific attributes inside that structure, you use the dot to dereference it. So the name of wherever that attribute or method resides in, dot the specific attribute or name. Okay, so looking at other parts of this class right here. Oh, okay, so by the way, there's also something not explicitly shown here that Python automatically does. The method init right here will implicitly return an instance to self right there. You just imagine that part, because the call to init right here, when you're doing it outside the class, at the end of the initialization, you're basically storing whatever the prepared self is to the instance that is it being instantiated. That will be clearer when we actually perform these lines right here. So to use the init function, we create two instances of robot using the following code. So these two right here. So let's uncomment these ones. These two, sorry. Save them. Okay, so what is going on right here? So to use the init function, you don't actually call the init function like this. You don't invoke it using its init name, blah, blah, blah. To invoke it, you use this specific invocation. So starting at the first line, the identifier R1 is assigned a new instance of robot named Bonk, and the identifier R2, which you can find in the second line right here, is instantiated with a new instance of robot called Chunk. The expression robot bank is equivalent to invoking the init function. This expression right here, that is equivalent to invoking underscore underscore init. Oops, there are more underscores there. So whenever you see this way of instantiating, you're using robot right here. What you're doing is you're calling the init function found inside the robot class. So notice how init, if you remember, in its definition, it expects two things. It expects the self and it expects the parameter n as well. But its invocation only contains one parameter or one argument being passed, namely just the name bonk itself. That is because the instance assigned to self is automatically passed without being explicitly shown. Which instance is assigned to self? This R1 right here. This R1 is automatically referenced by self, or the first thing that is implicitly passed to init. And again, this becomes a sort of a lot of this becomes a source of confusion because a lot of people forget about the hidden self right here that you always pass whenever you're calling a method in a non-static manner. So including me from time to time, I sometimes forget that there's an implicit self right here, and sometimes I forget to add self right here in the definition of init and other methods. So since there are two separate instances of robot with different names, what is going to happen for the first instantiation right here, again, R1 right here, it is passed to self right here, and this bonk string right here is referenced or assigned to the parameter n that you see right there. And inside initialization, what you're doing is simply creating an attribute called name and giving that to self, which is again a reference to R1. So R1 dot name becomes the value n, which is what you passed a while ago. In this case is bonk. A similar thing happens to the second line, but instead of bonk, you're assigning it the name chunk instead. Okay, so just to take a look at what is going on when you do that. I've also created these other methods right here. The first method is called talk, right there. Notice how this talk right here also uses a special instance called self right here. Again, self, which is the first and only parameter being passed. And it is used by concatenating self.name right here. So since self refers to the instance invoking talk, the instance's own name is used. So that would be bonk for R1 and chonk for R2, depending on which self is invoking this talk method. So also notice how when invoked, nothing is passed to talk. So I haven't uncommented it so far right now, but if you notice the invocation to talk, r1.talk right here, you don't pass any value, but the definition for talk expects a self to be passed. Again, this self is automatically referenced to whoever is invoking this method. In this case, the one invoking this method is the instance of robot called R1. So whenever you're writing a non-static method, you should always include this self right here in the definition. Even if you do not use the reference to self inside the function, you should always do that because Python will force the first parameter in the method to accept the instance reference. So even though you do not use an instance of self, in this case we are using it, even though you don't you just print a normal string right here, you should always include the self parameter right there in its definition so that Python knows that the first parameter or the first parameter being passed is reserved for the self reference. Okay, so just to demo what is going on right here. So let's uncomment these lines r1.talk and r2.talk, save it and rerun everything. But before that, let me comment out these lines since we don't need them anymore. Okay, so if you notice right here, let me go down there. So you have two prints. The first one is howdy, it's me, Bonk, and that print would refer to this line of code, r1.talk. So meaning the specific instance that is talking right now is the reference, or sorry, the instance of a robot called r1. And since that r1 is named Bonk, when you call communicate, or sorry, when you call talk right here, what is being concatenated to the string howdy, it's me is r1.name, which is specifically Bonk. On the other hand, on the second line, when you invoke r2.talk, r2 is an instance of robot again, but specifically its name attribute is chunk. Therefore, the second line will print howdy, it's me, and its name chunk, giving you that line right there. Okay. Moving on to the next lines of code right here, you have r1.name is equal to donk, and then r2.communicate r1. So first, the name of the instance assigned to r1 is changed from bonk to donk. This is what's going on right here when you perform this line right here. What this line refers to is a manipulation or an reassignment or a mutation of the r1 attribute called donk. So originally, r1.name's value was bonk. By reassigning it to donk right here, it will change r1.name to donk. So when you call r2.communicate, you should expect that what is gonna be printed is howdy donk, it's me, chunk. And if we dissect how this string is printed, you'll notice right here, you're using two different instances of robot inside the function communicate. So what the function communicate is supposed to do is it accepts another robot as its partner, right there, typed robot, and it prints howdy. Whatever is the name of the partner is concatenated there, and then whatever is the name of itself, it is concatenated here. So the partners, you're not passing the partner's name, right? What you're passing is the whole robot partner itself, which is R1. Because it makes sense. You're not communicating to a name, you're communicating to an actual robot. So what you should pass right here is the whole partner. But you don't actually need the whole partner. You just need partner.name to be concatenated here. So you dereference partner.name. And partner right here refers to R1. And R1's name has now been reassigned to donk. Therefore, you see the string donk concatenated there. On the other hand, the other robot reference right here is called self, which is again implicitly passed as the reference invoking communicate. In this case, that would be R2. R2's name is still chunk since you haven't changed it so far. Therefore, it is concatenated with the string chunk, giving you the whole string, howdy donk, it's me, chunk. Another important thing that you might notice right here, This is, if you notice the type annotation that I added for partner right here, I have surrounded it with single quotes. If you remove the single quotes for this specific annotation, you will actually cause an error. Let me demonstrate what's going on right here, why I need to add these. So if I remove that and try to rerun the code, you'll notice it has an error. It's saying that robot is not defined. So the reason why this Python right here is giving you an error that robot is not defined because communicate is inside the scope of robot. So robot is still not being done, is still not done being defined right here because you haven't exited robot yet. Therefore, using a reference to the type robot right here will cause an error because robot has not yet defined. It is still in the process of being defined. So to avoid that error right there, you can add this one right here, these single quotes. You will there are a lot of cases where uh, this specific error will come up, and I want you to remember this when you're doing your lab exercises because you might be confused this error is what this error means right here. And what this error means is just that when you're using the type itself inside the class that you're using it, so robot being used inside robot, it will not recognize robot yet because robot is still in the process of being built. Robot is still in the process of being defined. So you add these extra single quotes right here to avoid that. Okay. So let's talk about Python realizations and specializations right now. So you have here the syntax of establishing realization and specialization relationships are actually the same in Python. It actually just depends if the classes involved are abstractions or generalizations. So here's the generalization relationship in action. You can see it for class Skybot right here. There you go. So class Skybot right there contains a definition to fly. And if you try running these lines right here, I'm gonna uncomment them. And while I'm doing that, I'm gonna comment out all the things that we don't need so far. This one that doesn't actually print anything. This one and this one. So if we try to run this line of code right here, howdy, it's me, Zonk. I'm 3 meters high in the air. Skybot go zoom. So let's dissect what is actually going on right here. Note that, sorry, if you look at the class Skybot right here, it contains this method called fly. And note that even though self is unused inside here, right, there's no instance that uses self, you still include it in the list of parameters that it expects because again, it will always expect the first parameter to be an instance to the invoking class. The invoking instance. It is a reference to the invoking instance for Skybot. Because if you remove this, for example, what is going to happen is that it's gonna bind this instance right here. Let's not talk, it's fly. It is gonna bind this invoking instance right here to height. And you're gonna have a problem trying to concatenate height right there. So this is just a simple function. All you're doing is printing I'm height meters high. And if you notice right here, you're not concatenating height automatically with these string literals right here because if you remember or if you notice, the type of height is integer. So Python cannot make sense of adding or concatenating string with integers. So before you concatenate it, what you should do first is to prepare this by converting it into a string. And to convert an integer to a string, all you have to do is to call the str function. Uh, in fact, other types are converted in the same way. You just have to call the str function, and Python will automatically convert whatever type that is to a string. Well, it will depend if that specific type has a string conversion. So in this case, ints have a string conversion. So converting the height integer to a string is done by, again, calling the str function. This is a built-in function for Python. You don't have to import anything for this one. So by establishing this one right here, skybot parenthesis robot, the class skybot becomes a specialization of robot. And it is done through that line right there. The class name in between the parentheses will be specialized by the class outside the parentheses. So the class inside this one is the generalization to skybot, or skybot is a specialization of robot. And if you remember, what is going to happen if you establish a specialization relationship? Notice how even though the functions in it, the constructor that's in it, the function talk and the function communicate, these functions, even though you cannot find it in the definition or in the scope of class skybot, they are still, or skybot is still able to use these three right here because they are automatically being inherited by skybot through the specialization relationship. Just by adding this line right here, you do not have to rewrite these functions. So if class relationships haven't watched that video yet, you need to watch that to understand this part right here. So that's the reason why when I'm calling r3.talk right here, it will not cause an error saying that, oops, I do not recognize that talk method. I do not have that in my definition. It will still work because talk is, again, automatically being inherited by skybot from robot. The same is true for communicate, although I'm not doing it here. Let's try to do that. Communicate. So if you add r3.communicate and pass one of the robot instances that we have added a while ago, save that and then rerun it, it will have no problem communicating with R1 or Zonk, or sorry, Donk. If you notice right here, it still works, the communication part, because again, it is automatically being inherited by skybot through the specialization relationship. Another special thing right here, if you remember, what what communicate accepts is any robot, right? If you go back to the definition of communicate function, the partners type right here that you pass inside communicate must be robot. What do you think would happen if instead of passing an instance of a robot, I pass an instance of a skybot? r3.communicate to r3. Does it complain saying that it is expecting a robot and you're passing it a skybot? So if you run this one, what's going on right here is that skybot r3 named Zonk is communicating with itself, and you'll notice that it doesn't give you an error. So, oops, I just erased it. Howdy, Zonk, it's me, Zonk. It's talking to itself. And the reason why it doesn't cause an error because R3 is also a robot. It is both a skybot and a robot because skybots are automatically robots through specialization. Does that make sense? That makes sense to me. So here's an example that shows how to extend. Here are more examples that shows how to extend the attributes of a generalization. So what we did right here is that we're extending the methods of robot. We're extending it to contain the method fly. We can also extend the attributes of your robot. And if you notice right here, we can do that for this example, shadebot. So shadebot is another specialization of robot, and you know that to be true because of this line right here. By adding this line or by adding this parenthesis robot right here, you're saying that shadebot is a specialization of robot. Okay. So before we dissect this, let us run this part. Let me uncomment these things right here and comment out the things that we don't need right here. Talk, communicate, and fly. Let's hide that for now. Okay. So you just have 3 lines of execution right here. You have shadebot instance called tonk. You have r4.talk, r4.communicate, r3. So saving it and running it again. So howdy, it's me, tonk. Howdy, it's me, tonk. That's the second line is, I can't see you, my shades are too dark. So let's dissect what is actually going on right here. So here, even though shadebot inherits init from robot, it actually has its own definition of init. And you can notice that here. So shadebot will automatically inherit init from robot, but if you do create a new init function, then it will create its own version of init itself. It will forget the previous init and replace it with its own definition. So when this is done, shadebot replaces robot's version of init with its own, and this specific thing that you're doing right here is called method overriding. Method overriding. So you will need to do this for init if you need to extend the class to have more attributes, because to add extra attributes, you need to add extra lines in the initialization or the init function. And you also override methods if you need something changed for the specializations as well. So we actually do that for communicate. But for now, let's look at init. So you'll notice the strange line of code right here, which is this part, robot.__init self, n, inside shadebot's init. What you're doing here is statically invoking robot's init function to reuse the code inside it. Statically invoking, again, it means that the class itself is invoking the method, not any instance. And that's why self right here is being explicitly passed. Calling this is actually similar to the following line of code. You can actually replace this line of code right here by the contents of robot.init. So I can replace this with self.name is equal to n. That has the same effect as the previous line of code. In fact, this when I override initialization functions, this is how I do it. But you might notice this specific line of code right here. This is how other people do it. And this is explicitly inheriting or specifically inheriting the code inside init. So you are calling init function. And again, you notice right here, this call to init right here explicitly passes self. That's because this is a static call. That is a static call because you are dot referencing the class robot itself, not a specific instance. Okay? So again, you can interpret this part right here as just copy whatever parent initializes. So by adding this line, you're copying whatever parent initializes, and what parent initializes is the name. And this is where the extensions for the attributes are added. So since shadebot has shades, for example, you need to add a new attribute for visor opacity, which is a float from between 0 to 1. which tells you how opaque robots, or sorry, how opaque this instance of shadebot's shades are. So if it is 1, it is very opaque. If it is 0, it is transparent. So this is where you extend the attributes of a class. So if you're not changing anything that happens during the init specialization or just extending it, then you can statically invoke the generalization init. Otherwise, if you need to change how the specialization gets its name, for example, then you have to fully write the whole specializations in it. Okay? So, for example, if you want to change a robot that the way init prepares its name, for example, if you want to concatenate it with a name, you have to specifically write it there if you need to change how the initialization is being done. So for example, if I want the names of shadebots to be prefixed with Mr., so I have to incorporate that change itself to something like this. Mr. that concatenated with the name N. Okay? There you go. Running it again to see what the changes will be. So if you notice, the talk function now prints howdy, it's me, Mr. Tonk. And the next line, howdy, it's me, Mr. Tonk. Sorry, I can't see you. My shades are too dark. Actually, I forgot to dissect what the communicate override right here does. If you remember, communicate is automatically being inherited by shadebot because communicate also exists inside the generalization robot. But by creating this function right here, which is also called communicate, you are overriding communicate from robot. And you now have a new versions for communicate. And you do this if you need to change how the robot communicates, if it is a shadebot. So, and for me, I want a new behavior for communication right here because if the visor's opacity is greater than or equal to 1, meaning if the shades of the instance of shadebot is opaque, then it won't be able to see the partner. It says, sorry, I can't see you. My shades are too dark. If its opacity is not greater than or equal to 1, meaning it can still see the other partner, then it prints it correctly, the same way robot prints it. Great. So moving on. So those are examples of realization and specialization. Also, by the way, so another one right here, if you notice, communicate. Oops. If you notice communicate right here, what is being passed in this invocation of communicate is R3. And if you remember, R3 is an instance of Skybot. And again, this will still work even though partner is expected to be a robot because because R3 is both a Skybot and at the same time a robot as well. This is object-oriented programming's polymorphism in action. It is a robot, it is treated as a robot, but it will behave as a Skybot. Again, so that's it. That is a realization or a specialization relationship, sorry. Here, the next example that I'm going to show you is a realization relationship. Let's comment out these things since we won't need that for the other examples. So moving on, the syntax for realization is just the same as specialization. If you put an abstraction inside the parentheses, then the relationship becomes realization. So before we talk about the relationship itself, let's talk about an example of an abstraction because there's a difference in you need to properly create an abstraction to create a realization relationship. Okay, so first things first, to be able to make use of abstractions, you actually need a special import to a special library called the ABC library. And we specifically need two things, which is ABC and the abstract method decorator. So this is the import right here that is important for us. So from ABC, import two things, namely ABC and abstract method. ABC right here refers to abstract base class. And abstract method is the decorator abstract method that you use to indicate that these specific methods are abstract methods. And you typically put import lines at the top of your code above everything else so that uh, everything else in your code will be able to use these imported classes and decorators. So going back, you have barbell item right here, and the way we create abstractions in Python is by realizing the class we have just imported, which is ABC or abstract base class. So the abstraction in this case is the class called borrowable item. And for a class to become an abstraction, it needs to realize the imported class ABC. Hence, this line right here, borrowable item parenthesis ABC. By doing this, you're officially making borrowable item an abstraction. And if in Python, if you do this, what it means is that you are able to use this at abstract method decorator. So inside borrowable item are two methods called borrow and name right here. This is actually not included. That's for another example. Let me comment that out for now. There you go. So you have here two abstract methods called borrow and name. And you see this decoration right here, decoration, not declaration, called at abstract method. And uh, by adding this decoration right here, you're basically saying that the method that you can find below the decoration is an abstract method. What does that mean? We're going to talk about this later. So inside the borrow and name methods, you only see pass. Pass again, meaning that there is nothing that exists inside this scope, meaning the functions borrow and name do not have bodies. So they do not contain any implementation or body. You can put code inside these methods. You're free to do that, but it wouldn't matter. It would be useless since these methods will be guaranteed to be overwritten by borrowable items realizations. So let's talk about borrowable items realizations. So, oh, by the way, what abstract method does actually, or before we talk about that, let's talk about the realizations first. So the realizations for borrowable item right here is the class called book. And again, to establish the realization relationship right here, all you have to do is to add this line right here, book, borrowable item. Same syntax for specialization. And this will become a realization because borrowable item is an abstraction. Therefore, what this line establishes, instead of a specialization relationship, it establishes a realization relationship because borrowable item is an abstraction. It is not a concrete class. So inside that, you notice right here, init and borrow name. So this borrow and this name right here are actually required to exist inside book. If you realize an abstraction, you are required to override the methods or the abstract methods that you can find inside the borrowable item. So the abstract methods that you can find inside borrowable item are the methods borrow and name. So as an example right here, if I'm gonna add here a new method called implementation requirement, and I'm gonna add right here a decorator at abstract method, you'll notice that once we reach this part of the code right here where we instantiate a borrowable item right there, you'll notice that we will get some kind of error. Let me run that. And you notice right here, this is the error that you're going to see. So type error, can't instantiate abstract class book with abstract methods implementation requirement. You will encounter this error right here if you forget to implement abstract methods. So what we did to force this error right here was to add implementation requirement with a decorator abstract method. So since this is now an implementation requirement due to the abstract method decoration, then book must implement that as well. Book and IMAC unit, all the realizations of borrowable item. So to remove that error, you have to create its own version of implementation requirement. So just to show how the error is removed, there you go. And to add that to the IMAC unit right here, there you go. So saving and rerunning it, you'll notice there are no more errors. There are no more errors because implementation requirement has been implemented inside the realizations of your borrowable items. And whenever you want, oops, let me remove them again. Whenever you want a method to be an implementation requirement, if you want this method to be required inside the realizations of the abstraction, then you have to add the decorator abstract method. If you forget to add this decorator right here, then Python will not treat this method right here as an abstract method. Therefore, even though book right here, which is a realization of borrowable item, it does not contain implementation requirement, this will not cause an error because you have forgotten to add the at abstract method decoration. So what at abstract method actually does is it indicates to Python that the method directly below must be overridden by the abstraction's realization. Overridden, or basically uh, it must be implemented by the realizations. It must also exist inside the domain, or sorry, inside the scope of your realizations. So you'll notice this change again. If you remove that, it will remove the error as well. So we actually don't need this. This is just a demonstration of what abstract method does. So I'm going to remove that. There you go. Okay. So while I'm there, I'm gonna uncomment these ones right here, b.borrow and i.borrow. So before we trace what's going on right here, let's discuss what we're actually doing outside the class level. So what we're doing is we are creating an instance of a book. The instance of a book right here, this is of type borrowable item. Pero specifically, what borrowable item is it? It is an instance of a book. And to make it an instance of a book, we just instantiate it with the constructor for book right there. And IMAC unit, on the other hand, right here, we also create an instance of that and call it I right here. But the type we're using for that is borrowable item. And what's going to happen after that, we're going to borrow those books using the method b.borrow and i.borrow. So when you call b.borrow, it prints, I'm a book called Necronomicon and I'm being borrowed. When you print the second line, i.borrow, or when you call the second borrow function, i.borrow, you print, I'm an IMAC called IMAC5 and I'm being borrowed. So what is actually going on within the borrow methods? So moving on to these realization definitions right here, you see that each realization overrides the abstract methods borrow and return. And also note, by the way, before we move on to that, the code inside books init, although the parameter is called title right here. Oops, yeah. The parameter is called title and the attribute is called title. Python can actually differentiate between these two titles right here because one title is the reference using self, while the non-dot reference title that you see right here is the title that refers to the parameter called title because it doesn't have a dot reference to anything. It is fine to do this, especially if you want to emphasize which parameters are stored to which attributes. In fact, I actually quite do this a lot. You'll notice this, that the parameter that I'm using to be stored to an attribute will have the same name as the attribute itself. So this is title, this is also title, but again, they are differentiated by the dereference self right here. The one dereferenced with self refers to the attribute owned by self, while the one without dot referencing is the parameter called title. Okay, so you might get confused if I see my code. Also, another note, the abstraction borrowable item doesn't have this init function. And you might probably expect that because this is because borrowable item is not meant to be spawned or instantiated. You'll notice right here. It doesn't have an init function. It doesn't have a constructor. It is not meant to be spawned or instantiated. It is merely an abstraction. So therefore, it must be ethereal and formless. It is just an abstract thing. So what is actually going on inside the borrow functions of each of these realizations? So it is actually different for book and iMac unit. For book, the way that you borrow book is you print it this way. I'm a book called self.name and I'm being borrowed. Actually, it's actually similar to this borrow right here. Oh, here's the difference. This specific string literal right here. Although it's a very minor difference, it is a difference between the borrows. So the borrow for book says I'm a book, while the borrow for iMac says I'm an iMac. And outside the class scopes, you'll see the borrowable items instantiated like that below. Let me remove that and go back to outside the class. So if you notice, I forgot to discuss this part. Both B and I right here are instantiated to be of type borrowable item, right? They are annotated to be of type borrowable item, but they're instantiated specifically to be book or iMac unit. Meaning B and I are treated as borrowable items, but they will behave as iMac unit and book. And that's realization in action. Moving on, Python visibility control. Another important Python syntax to remember is how to simulate different visibility levels for methods and attributes. So this is how Python implements its data hiding capabilities. Given the following class below called clandestine class, notice how attributes and methods have special prefixes. These prefixes will tell you their visibility levels. So clandestine class, inside its initialization, it has three different attributes. They're just integers. One is called public value, the other is called underscore protected value. The last one is called underscore underscore private value. All you have to do inside their constructor is that you pass three integers, public value, protected value, and then store them to all three of these attributes. They also have methods as well with the same prefixes. The method do publicly doesn't have a prefix. The method do protectedly has a underscore prefix, and the method underscore underscore do privately has two underscores as prefixes. So what is actually going on right here? So when the following code is ran, before I forget, let me uncomment these ones so that it will not clutter up our terminal. There you go. So what is actually going on right here? You have here a print to the values inside clandestine class. You have print public value, you have print protected value, and print private value. Let's remove this for now. There you go. So what is going to happen if you rerun this code right here after saving it? It's going to complain that this specific line right here, print c dot private value, the object has no attribute underscore underscore private value. When in fact, if you look at the definition, it does actually contain an underscore underscore private value. For some reason, Python cannot see it. In other OOP languages, by the way, before that, where was I? So what is going on right here, the reason why it is able to print 1 and 2, which are the public value and protected value, it is able to print that, but not private value, is because of the special prefix that you add for the name of private value. By adding these two underscores right here, you're basically telling Python that this attribute right here is a private thing, meaning it can only be accessed when you're inside the class itself. When you're outside the class, it won't recognize that as a value. Therefore, Python will complain that it does not recognize that as a value. It cannot find that in its attributes. So when you are outside the scope of a clandestine class, for example here, we are outside the scope of clandestine class, private value right here is not recognized because it is again private. It is only meant for the eyes of clandestine class itself. But whenever you're inside the scope of clandestine class, so for example, you're here, when you call do publicly, you'll notice that these three lines of print right here will not cause an error because even though you're accessing a private value, you're accessing it inside the context or inside the scope of the class itself. So I'm going to comment out this print right here because this causes an error. And I'm going to uncomment this out. Actually, in fact, I'm going to comment these three na lang. So if I save and rerun this one, hey, these are my values, 1, 2, and 3. It is now able to print 3 because you are printing it inside the scope of do publicly, which is inside the scope of clandestine class. By the way, this is a little bit of a Python specific thing. In other OOP-based languages, protected values are also not supposed to be accessible outside the class, but Python actually doesn't have the protected mechanism. So the protected value right here that you see, which is prefixed by this underscore right here, protected value, other programming languages, other OOP languages like Java and C++, for example, protected values will also not be accessed outside the scope of that class. But Python doesn't have that mechanism. What Python programmers do instead as a fix for that is to write protected identifiers with a single underscore prefix that you see right here. It is not an official feature thing. Yes, you can still access them, but this underscore right here is an unwritten rule for Python programmers that says na you're not supposed to access this outside. Okay, another thing, specializations also do not have access to the private attributes and methods of its generalizations, but both public and protected are accessed. If you want some attributes or methods to be inherited, but still sort of inaccessible outside, you make them protected instead. So this is the actual use for protected attributes and methods. So you have here special clandestine class right here, which is a specialization of clandestine class. And if you remember, we established that relationship using this syntax right here. So it will automatically inherit in it and its attributes public value, protected value, and private value. So if we, let me comment this out and let me uncomment this out, s.do publicly and s.do something special. So s.do something special right here is the extended method that does not exist outside of clandestine class, the special method right here. Okay, so for the first one right here, what's going on? When you call s.do publicly, you'll notice that, oops, let me erase that. You'll notice that all of these three things right here are printed. The public value, the protected value, and the private value. Because do publicly, again, is a function that exists inside the scope of clandestine class. Therefore, that function is able to access all three levels of visibility: public, protected, and private. So public, protected, and private, although they are inherited by clandestine class, or sorry, because although they are inherited by special clandestine class, they are still uh, they still exist inside the scope of the general class clandestine class. This one right here, they exist inside this scope. So whenever you do something like this, do something special, and just to look at what do something special does is actually very similar to uh, do something. So it still prints three different values right here. You know what? Let me just to differentiate the two. Let's add another line of print right here. You know what? There you go. Special clandestine. There you go. If I save this and rerun it, so do something inside special clandestine class right here. This call will now have an error. The first one, the public value, will be printed. The second one, the protected value. And finally, the private value right here will cause an error because, again, the private value, which is called underscore underscore private value, this one right here, exists inside the scope of clandestine class. Even though it is inherited by special clandestine class, it is still an attribute of clandestine class. Therefore, Python will complain if you access that inside special clandestine class because special clandestine class is outside the scope of the general clandestine class. So if you look at the lecture notes I have for this one, there's a summary for the access rules, the differentiations for public, protected, and private. You don't see it here, but maybe it's here. I have it open. I do have it open. So here's a summary of access rules. So public values right here don't have prefixes, and it can be accessed by specializations, yes. It can be accessed by clients, yes. Protected values, it can be accessed by specializations, yes. It can be accessed by clients, technically, yes. But you're not supposed to. It's like an unwritten rule that underscore right here means protected, meaning you're not supposed to access this outside the class itself or the client classes that are dependent on that. Private values are not able to be accessed outside the accessed by specializations, and it can also be accessed by the clients themselves. So this is an increasing level of privacy or a decreasing level of visibility. So the rule of thumb right here, if you want something to be public, if you want this to be accessed by client classes and specializations, then you don't add a prefix. If you don't want it to be accessed by clients and you don't want it to be accessed by the specializations of that class, then you add double underscores. But if you don't want it to be accessed by the clients, pero you still want it to be accessed by specializations, then you add a single underscore, making it protected. And that is all for this Python OOP syntax lecture. Thank you, everyone.